All right, welcome back. Do we have any more questions? Or I said that I would give you an example of a very simple non-simply connected manifold, right? Is everyone back?
I'm here.
Yes.
Yes, sir.
Okay. Okay. All right. So, so the most simple non-simply connected manifold is actually a circle, because consider a loop on a circle. What is the simplest loop on a circle? It's a circle, right? So let me just draw the circle, the loop over here. Okay. Right? So that's an example. So so can we actually shrink? Actually, that's not a good way of doing it, I think. Yeah. So if you consider closed paths on the circle, say, which goes from a point back to the point itself, is that a, can you actually shrink that down continuously to a point?
No.
No, right? But if you say go in this direction and then come back over here, then that can be shrunk to a point, right?
I was actually wondering about this. Isn't this a self-intersecting path, technically?
Yes, yes, it is. So the rigorous way of defining these things is actually in a slightly different way. And I was, so what we consider is all the maps from the circle to whatever manifold we're considering. Okay, so we consider all the maps, and but the map is actually not just the map times some interval. Okay, so this map is going to has some parameter, say t, which is sorry, it should go around, which is the parameter for the interval, and the circle, which we can say theta, right? So this gives me a point on the manifold. Okay? So what does this, what does this T kind of signify? So the T signifies essentially it signifies something like this. So so it is telling you how we are deforming this map. So if suppose this is our first circle, and this is, say, T, and this is our manifold. So if I am, say, at T equals to 1, the map is going to be this circle. But if T is 0, then suppose that then the map is going to be this point. This is not like technically rigorous, because I would have to look up what the right way of defining these so-called homotopy groups are. But what will happen is that as you change the T parameter, what happens is that the map from this, the map from the circle to this manifold, which is, a closed loop, that changes continuously.
So it's like a slider that's playing a movie.
Exactly. And this slider can be, kind of multidimensional or something, because I think so, because it just captures how many different ways you can continuously, change this map. Okay. So from this point of view, we actually don't care about, do we care about self-intersecting curves? Let me just, no, actually we don't, I think. I don't think we do, yeah. So that's also, because, as you go around the circle, you are just, it's completely well-defined how you're moving over here, right?
So each point is associated with a unique t. Oh,
Exactly.
no. Yeah.
Well, for every, no, that's not true. For every t, you have to have, the map doesn't have to be invertible or anything, right? So it doesn't have to be, one-to-one.
Oh, right. So every t is associated with a different step towards one of the sides of the map.
Yeah. T is a parameter which tells you where you are on your, sorry, it's not t, it's a theta. The t is telling you what the shape of the circle is. Okay. The shape of the loop is. It's as theta goes from 0 to 2 pi, you are moving on this loop. Now, there are other loops possible. So for example, let's take a map. Suppose that, so suppose we're in higher dimension where there is no intersection. So that is also possible, right? That is also a loop, right?
Yeah.
I mean, this is also a loop. This is also a loop, right? So now let's take, so this will be qualitative. If you want more quantitative stuff, I can provide you. Suppose that M is my target manifold is also a circle. Then there could be maps from, say, S1 to S1, where as you move from 0 to 2 pi, you move from 0 to 2 pi on the circle. But there could be maps where as you move from 0 to 2 pi, here you move 0 to pi. Okay? And as you move again from 0 to 2 pi, you come back to the original point. That's not interesting. Actually, what I wanted was that the maps that move more quickly. So essentially, as you go from here to pi, that's what I want, sorry. So as you go from 0 to pi in the original circle, you move on the target circle from 0 to 2 pi. And then as you move from pi to 0 on the original circle, you then move again and then come back to the same point. So for the circle, this is a map which winds around the circle twice. So we say that the winding of this map, the winding number is 2. Okay? Does that make sense?
Yeah.
So there could be an infinite number of winding. So we see that for the circle, like if you wind around once, that gives you a map which does not shrink down to a point. But the map which winds around twice, that map cannot be deformed into a map that winds around once. So the number of maps from the circle to the circle, there are an infinite number of them, And each class of map is, each class of map is characterized by an integer, say n. So we say that, and this can be given a group structure, a abelian group structure, basically the composition of loops, but I won't go into that. But essentially, we say that the first homotopy group, the first homotopy group of the circle is Z2, by which we mean that the maps from the circle to another circle.
Sir, won't it be Z, the homotopy group, because we can characterize by all integers?
Yeah, sorry, Z and not Z2. Yeah, sorry. And you might say, okay, I've seen the positive, but what about the negative numbers? The negative numbers, so, we can make the convention that on our original, this circle, we only go in the counterclockwise fashion. But there is another map, which is actually the F inverse map, which as we go around here, the clockwise fashion here, we go in the counterclockwise fashion. If we have the winding n for this map and the winding n, then we can say F inverse n is F of minus n, such that F of n, F of minus n is 1. Okay, so what is this group composition law? It's basically if you go around one circle and in one direction, and you have another circle in your target manifold, you go like that. So this is map number F number 1. So let's call it F, the map F, and this is F prime. And this is F, you go around F first and then F prime, F first and F prime second. This is the composition. Okay, and you can see geometrically, it's, this is going to be abelian. Okay, so this is effectively the group, and the trivial map where you just don't do anything, where you go around the circle but you don't move on the target circle, that is the identity map. So so basically any path which starts at this point but doesn't go around the whole circle and comes back, that's in that class of identity maps. So, and this is known as the fundamental group, fundamental homotopy group. Now, this is very qualitative, but you can show that, you can argue that this is trivial, right? That the maps from the circle, the continuous maps from the circle to the real line is going to be trivial. And we have just argued that the maps from the circle to the circle is characterized by all the integers, but the maps from the circle to, say, the two-sphere is just the identity map. And in fact, for any circle, any sphere for n greater than 1 this is true. So this
I have a question.
Yeah.
Yeah, so if you were to describe this fundamental homotopy group in an intuitive way, what would it really mean? What does it characterize?
It characterizes the equivalence class of maps from S1 to your manifold. It characterizes the equivalence class of continuous maps from S1 to a manifold. Okay, so pi 1 characterizes the equivalence So equivalence class of continuous maps from S1 into, so pi1 of M into some manifold M. This actually is not just for manifold, it's also for shapes I don't know, yeah, but you know, that's more technical, and you know, and I'm not really the right person to talk about that. Okay, Nahi?
Okay, sir.
This can be generalized. This can be generalized to Sn of some manifold. And these would be maps from Sn to some manifold. Okay, the continuous, some parameter space, I cross. Okay.
I have a question.
Yeah.
So I've heard that there is a geometrical interpretation for the homotopy groups, and that they characterize the number of n-dimensional holes that the space has. So pi1 would be the number of one-dimensional holes that the space has. So the circle has one-dimensional hole.
Yeah, I mean, that's a roughly speaking.
Sir,
That's
what does
basically
it mean to speak of a dimensionality of a whole?
Yeah, I'm not exactly sure. Yeah, I mean, for example, if you look at, say, a torus, torus also has its, you know, pi1 of, what is a pi1 of a torus? A 2 torus is going to be
Z plus Z, I think so.
Zn cross Zn, right? Because they're 2 circles. A torus is essentially 2 circles, right? So, you know, whereas if you have a 2 sphere, you know, S2, then we have, so, you know, so Saifia, I'm not sure if you're right, because the circle does have like a hole in it, right? Here. But so does, you know, it only looks like a hole because we're embedding the circle in a 2-dimensional space. So if I take S2 and I embed it in, say, R4. So I embed our S2 in an R4, then, you know, suppose this S2 is your head. And inside your head is your brain. Because, you know, if we embed it in R3, which is our space, you know, the brain cannot get out. It stays snug in your head. But if I add another dimension, right? So then in R4, there your brain can pop out of your head.
Similar to, we can like put our hand through a ring.
Yeah, exactly. So what I'm trying to say is that, you know, what Saif was saying that, oh, S1 has a hole. It's an artifact. The fact that S1 looks like it has a hole is an artifact of the fact that we're embedding the S1 in an R2. And for whatever sphere, if you go to 2 more dimension, then you can always see that that thing has a hole in it. But, you know, but it does not make the 2 spheres simply connected. But what happens here is that now we have to generalize the idea, right? The idea is that what if I now consider the map from the 2 sphere to the 2 sphere? What if I look at pi2 of S2? And there, I think this is true. I'm not exactly sure. Let me look that up, because that's a very, these are theorems that I never studied, but, you know, they are important for physics, especially condensed matter physics and cosmology. But I never studied there's a whole sort of, you know, list of these groups called the bot, and there's like a periodicity to them called the bot periodicity and blah blah. But let me just look that up. What is the pi2? Pi2 of S2. Right? Yeah, pi1 of S2 is of course just yeah, pi2 of S2 is it is Z, yes, exactly. I keep writing Zn, it's not Zn, just Z. Sorry.
Yeah, so
Zn is a different.
Yeah, Zn, yeah, sorry, it's Z.
according to the geometrical interpretation that I was reading,
Yeah.
two-dimensional holes are cavities. So the torus and the sphere have one two-dimensional hole because they have a cavity in them.
Okay, I mean, if I'm not familiar with that terminology, but yeah, that makes sense.
I mean, there's nothing inside the torus because it's just a surface, and unlike a donut, which has a filling inside.
Yes, I mean it's. But you see,
in another sense, if we think of the construction of a torus, there is something inside the rectangular boundary, right?
Yes, but you know, I am more akin to thinking of a manifold without reference to embedding.
Yeah, sure. This interpretation only works if you embed it into a higher.
Yeah, and embeddings can be very arbitrary, right? I mean, you know, for example, the Klein bottle, right? I mean, we can't embed the Klein bottle in three dimensions. That's a good example of a two-dimensional surface that cannot be embedded in three-dimensional Euclidean space, right?
Yeah.
And there are even like space-times which cannot be embedded in Minkowski space with one-time dimension. And the anti de Sitter space is one example of that. So there are all these, I mean, there's actually a very interesting theorem, embedding theorem. And this, I think, it's actually the guy who got the Nobel Prize for economics, but really for mathematics. What was his name? The guy who
Nash.
Yeah, Nash. So Nash is famous for laying the foundation of game theory, which underpins a lot of modern geopolitical, you know, atomic warfare and things like that. But Nash's real contribution to mathematics was not game theory, but it was, well, that was of course game theory, but a more deeper contribution to mathematics was something called the Nash embedding theorem. And he figured out the general conditions under which some torus can be embedded in a higher dimensional manifold, or something like this. There's a very beautiful number file or a series of number file videos on the Nash embedding theorem. I will post that on Slack, okay?
Oh yeah, I watched a video where they showed that if you embed a torus in 4 dimensions, the idea that the torus is differently curved on the two sides, like the two curves are different lengths, goes away because it's an artifact of 3 dimensions.
Exactly. Yeah. So those are, you know, fun, you know, differential geometry topics.